Okay, good morning and welcome back to the lectures. Yesterday we talked about quantum computation. In the morning we talked about classical information. In the afternoon, no. In the morning we talked about classical computation. In the afternoon we talked about quantum computation. This whole quantum technology has two sections. One is computation, quantum computation, and the other one is information, quantum information. So in the spirit of yesterday, in the morning we talk about classical information, and in the afternoon we talk about quantum information, right? And then we start from intuitive arguments, and then gradually go toward more sophisticated arguments, but not to the rigorous theory, just to have the idea of what information is, right? Let's see. It's not working? This says that it works, but the pages do not come forward. Maybe the battery is I can come over there and answer from the comments. Well, we can forget about this. Yeah, it's better. Okay. No, I'm okay. No, thank you very much. Okay, you see that these data are not new and not up to date. Probably by today they have changed. Each second, there are 40,000 searches in Google each second. As you see, you always are doing searches in Google and other databases. And then each day, there are 3.5 billion searches in Google. You ask for information, you search information, and so on. And then the current capacity is 20 petabytes per day, or 20 million gigabytes per day. Information is added to Google, right? These are really huge numbers. And 100 exabyte is the current capacity of Google, which is equal to 1,000 billion gigabytes. Again, I stress that these data are not up to date. Every hour, every day, 4 million hours of new clips are added to YouTube. You watch these YouTubes, probably some of you also are adding movies and clips to YouTube. So we are living in the information age. To go to the more scientific part, there are huge telescopes working and surveying the skies. And one of them is this LSST. And each night it gathers data of this size, 50,000 gigabytes per night. You're gathering information of this huge size every night. And this is just one discipline of science. There are many disciplines of science, from biology, engineering, cosmology, astrophysics, and so on and so forth. For example, like the Human Genome Project, or all these sorts of things. So we are living in information age, and we are gathering and storing all these huge information to process them later and see the working of nature, the working of galaxies, stars, genome, and so on and so forth. We have to store this information someplace, right? You are always working with different files of your computer. They store it in, for example, Dropbox and so on. All this data should be stored somewhere, right? And this is a picture of one of these data storage facilities. And the point is that if you want to store something, and if you want to gather information, like any other quantity, you have to quantify it. How much information? We quantify everything that we deal with. We quantify mass, we quantify depth, we quantify momentum, energy, and so on. If you want to store information, you have to know how much information, right? So the basic problem is that we have to quantify and measure the information. That's the topic of today morning. How to quantify information? So we start from this very simple argument, quite intuitive argument. And the whole thing has been set up by Claude Shannon, who is the father of information theory. He wrote 2 papers in 1949 and 1948, and he laid the foundations of this science. And everything that has been written after Shannon has been ramifications and refinement of these 2 papers, expansion of these 2 papers. So he laid down the foundation of the whole theory, right? So let's start from these very simple and intuitive arguments, right? I can motivate you by this cup of coffee, right, to get to information and its relation to entropy and surprise, right? Suppose that I tell you one of these 2 sentences. A, tomorrow there will be a lecture in this institute, TBAE, right? This is the name of the institute, TBAE. The second sentence, tomorrow there will be a music festival in TBAE, right? By which sentence I will give you more information? What's your guess? The second, right? Because it's a rare event. You do not expect that, right? The second one has more information. You already know that there will be a lecture tomorrow, but you do not expect that there will be a festival. Now the second question. To which event do you rush into tomorrow? Be honest. The second one, okay? That's the fun part. So the second sentence has more information content, right? That's the basic idea. The more surprise that we get by getting some sentence, by getting some news, the more information we get, right? Because we expect those events which are more probable. They do not give us any new information. We already know that. So if you want to assign some information content, some quantity to these 2 sentences, call it H, we know that H of B, this sentence, is higher than H of A. Anything that we want to assign as a quantity information should have this property. This is the first criteria. Now let's go on, and this is again this statement in the last slide in figure. This is the probability of the event, and this is the event itself, and this is the information content that we want to assign. If A is less probable than B, then the H of this event should be higher than this. This is the first property. And then, suppose that I give you 2 sentences, 2 news, 2 pieces of news. A, tomorrow there will be a lecture in this institute, TDA, right? This is the statement A. B, tomorrow there will be a musical festival in Ankara, right? Then you expect that the information that I give you is the sum of these two informations, because these are two independent events, right? They do not depend on each other. So by saying these two statements to you, by conveying this information to you, I'm giving you two pieces of information, the sum of these two. This means that if an event, these two events are come together and they are independent, their probability is the product of the probabilities, because they are independent. P of AB is the product of PA and PB. These are the probabilities. So I expect that this information content, this information measure, has this property, that H of PA times PB is equal to H of PA plus H of P. Right? This is the second criteria. And if you think about this function, which function has this property? Right? Which continuous function has this property? Does anybody know the answer? The logarithm. The logarithm is the only function which is continuous and has this property. So the only function which happens to be the correct answer is this function. H of P should be some multiple of the logarithm. We do not know alpha. Alpha is an arbitrary constant. For any alpha, this property holds. So if you want to assign a quantity for the information, it should be equal to alpha, some constant number, times the logarithm of the probability of that quantity. Right? The more probability it is, the lower the information content, so alpha should be negative. And how do we determine alpha? How do we determine this constant? Then we come to the final point. The final point is that, like any other measure, you have to quantify the unit of measure, like the kilogram for the measure of unit of measure of mass, meter for the length, and so on and so forth. So we have to assign a unit, and the unit is assigned by this simple experiment. You have a coin with two outcomes. The outcomes are equal. So any two outcome event is enough to take a coin. The probability, a fair coin, the probability of any two sides is equal to 1/2. And if I tell you that the head taken or the other side, the probability should be 1 bit. Sorry, the information content should be 1 bit. So we assign the name of also this unit. The name of unit of information is 1 bit. So I want that the function h should be such that h of 1/2 is equal to 1. Right? Because the probability of each of these two sides is 1/2, and I want that the function be a logarithm so that h of 1/2 is equal to 1. I mean that alpha times log of 1/2 should be equal to 1. It means that alpha should be -1. The log should be taken in the base of 2. So this is the information quantity that we assign for any function. If you have an event which has many, many outcomes, right? If you have an event which has many outcomes, x, with all these outcomes, with all these probabilities, and if I give you the information that this happened, or this happened, or this happened, then the average information that I'm giving you is given by this function. Because each event happens with the probability of px, right? This is the probability that one of these happens. And as a reporter, I'm giving you that this one happened, this one happened, this one happened. And then by each statement that I give to you, I give you log of px to the base 2 with some information, with minus sign. Then the whole information that I'm giving you by telling you all these statements is h of x. This is called the Shannon entropy. And this is the information content of an ensemble of events, of an ensemble of outcomes, right? I can stop here if there is any question, but then you can go on, or you can interrupt me at any moment that you like, right? This is called the Shannon information, Shannon entropy. Why it's called entropy? Because of these two reasons. Shannon consulted von Neumann, they were contemporary, and von Neumann taught him these two statements. First, this concept of entropy, this function has already been introduced in statistical mechanics in 19th century, and the second reason is more fun. Nobody knows what entropy is, right? So in any discussion you will have the upper hand, because entropy is an obscure concept. So it's better to name this entropy. This is the name that John von Neumann taught Shannon to call this function entropy. Why it is called entropy and why it's connected to what we know in the statistical mechanics, right? You know from statistical mechanics courses that entropy is a measure of disorder. The more entropy means that the more disorder. Low entropy means ordered configurations. So if you have such a configuration which is entirely ordered, and then you flip one of these two, and you want to predict the color, whether it's blue or red, you already know that it's red, because it's very ordered. So you have here zero entropy and complete information, complete order. And when you flip one of these coins, you get no information, right? Because you already know that all the balls are red, right? In this case, you have high entropy and minimum. But if I tell you one of these balls is blue or red, I'm giving you much more information because you do not know beforehand if it's blue or red. So high entropy means minimum order and high information. Low entropy means zero information or low information. That's why it's related to entropy, which was introduced in statistical mechanics tens of years ago, before Shannon, right? So in this sense, we connect information theory with statistical mechanics, right? And thermodynamics. If you study information, you will always be connecting these different ideas. Now let's go to a slightly higher level, right? A higher level of sophistication. Still, I stress that we do not go to the rigorous theory of information because it requires a lot of mathematics, but we can get the main ideas, right? So that you will be ready to read technical books on information. Okay? Any question up to now? The first Shannon theory, in fact, the whole information theory is based on two theories. The Shannon first theory and the Shannon second theory. This is the two pillars of information. The first theorem is how much information can be compressed, right? We want to communicate information from one place to another place. We have to compress it. We do not want to be generous in the amount of information that we say. Many of the talks, especially of politicians, can be compressed to a few words, right? There is no information content in these words. So it depends on how much content a statement, or a news, or a talk has, or a picture, or a sound. You can compress it. So the first important theorem of Carl Shannon is that how much you can compress it without losing the content, without losing the information. Because if you want to store this information someplace, you have to compress it, because you have to pay money for that, because you have to make facilities like those huge boxes that they showed you, right? You have to compress it as much as possible, because it costs you a lot. So let's see. Suppose that we have a source of information, a loudspeaker or something like that, which produces this sequence of letters, A, B, C, D, etc. Right? It's giving us some text or some sound or some music, and it contains only this sequence of letters of A, B, C, D, etc. And suppose that all these letters of A, B, C, and D appear with equal probabilities in the text. When you imagine and examine the whole text, you will see that all these letters appear with the same frequency, with the same probability. The probability of each letter is 1/4. In this case, the best thing that you can do is to encode A, B, C, and D to 0, 0, 0, 1, 1, 0, and 1. Right? There is no better way. All of them have equal probability, so you have to spend 2 bits per letter. It cannot be compressed more than this. You have to spend 2 bits per letter for storing this information. Okay? Now suppose that your text is like this, with these probabilities. The probabilities are now 1/2 for the letter A. A is more frequent than the others. B is 1/4. C and D are 1/8. If you sum these two probabilities, these 4 probabilities, you will see that the sum of all these probabilities is equal to 1. Right? You agree? Can we encode all these letters A, B, C, and D with a smaller number of bits of that? And then we can see that yes, we can. Let's see how. For this letter, which is more frequent, I spent only 1 bit. For these two, which are less frequent, I spent more number of bits. So I encode these letters in this way. I encode A to only 1 bit, 0. B to 1 and 0 to 2 bits. C and D to 3 bits. And you have to encode it in a specific way so that there is no ambiguity in decoding these bits to A, B, C, and D. Right? So I have saved something. I have saved the number of bits because for this letter, which is highly probable and appears many times, I'm using just 1 bit at the expense of using 3 bits for these 2 letters, which are less frequent. Right? On the average, I'm saving some number of bits. And you can probably guess that there is a relation between the number of bits here and these probabilities. Can anybody guess what is the relation? Yes, exactly. If you take the logarithm of this, logarithm of minus logarithm of this, it's the number of bits. Logarithm of 1/2 at the base 2, with minus is 1. Logarithm of this 1/4 at the base 2, by minus, it's 2, and so on and so on. That's exactly the case. So in this case, you can compress this, the same sentence as before, with a lower number of bits. In this way you save. And on the average, this is the relation between the length of each letter, the number of bits of each letter, and this is the relation with this probability, log of 1/p, or minus log of p, to the base 2. On the average, you are using 1.75 bits per letter. Instead of 2 bits, I'm using 1.75. You may say that 1.75 is not too different from 2, right? You may say this. But if you want to store billions and trillions of bits, it matters very much, right? So in this way, you have compressed this information. And that point, and that quantity that we found, is exactly the Shannon entropy. The average length that we found is 1 over logarithm of 1 over p times the probability of each event, of each letter, and then you come up with the function of Shannon. Because if I can write here, Li, which is the number of bits that you use for each letter, is log of 1 over pi to the base 2, or minus log of pi to the base 2. Each of these letters appears with a probability pi. So p of log of pi minus sum over I. This is the average length of bits that you are using per letter. And this is nothing but the function h of x, the Shannon entropy. Right? That's why this is the ultimate limit that we should compress, or we can compress. So the basic theorem of Shannon, without proof, is this. You can compress anything, no matter if it is a picture, or a sound, or a movie, or a talk, or anything, you can compress it below h of p. You cannot compress more than that. If I can store this picture of Mona Lisa, I can use smaller number of bits, and then I can recover this. And I tell you an experiment. I will leave these slides on the, this computer or the website of your institute, and then you will look at these two pictures, right? And then make a distance, look at these two distances from far away. You will not recognize which one is real and which one is compressed, right? From the near distance you recognize, but if you go far away, you will not recognize. Because these, for example, this area, it's all the same. It's not different from this area. So it's not necessary to use many bits for storing this area. You can coarse grain this area with lower number of pixels and store a little lower number of bits. So if you go far away, you will not recognize, because you do not see this coarse grain. But if you want to compress more than that, then you will find something like this, a Picasso painting of Mona Lisa. You will not recover the main picture, right? This is the whole idea. So h of x, which is the Shannon entropy, is the ultimate limit that you can compress and store information. For storing millions of bits, it's a very important technological advance. Again, copy. Any question? Questions? No? There are three here. Right? So, let's go a step a little bit higher than the previous one in sophistication. Right? The basic concept that we should learn, and we should pay attention to, is the concept of typical sequences. They are all the same. Surprise and probability is the lower level that we want to deal with information. Then we come to this coding, right? And then we come to this concept of typical sequences, which occur again and again in information. What it means to be typical sequence, right? Suppose that we have a number of bins, okay? A number of balls. And each of these balls can be blue or red. Suppose that we have n balls, right? How many total sequences can we have if we have n balls? I want an answer. How many sequences we have in total? 2 to the power n, right? Because each ball has 2 colors. We have n balls. So the whole number of possible sequences is 2 to the power n, right? You agree? Okay. now suppose that the probability of a blue bar is 1 minus p. The probability of a red bar is p, right? I may be boring you by these questions, but bear with me. So the average number of red balls, you agree that it is n times p. You agree? Because each ball, each red ball appears with a probability of p. On the average, for long sequences, not for short sequences, for long sequences, on the average, you have np red balls. Then you can say that if this is the average number of red balls, then typically, in each sequence, I should have np balls of red color, and the rest should be of blue colors. So how many typical sequences we have? Typically, how many typical sequences we have? A typical sequence is the sequence of balls in which there are only np red balls. Not, for example, 1 ball or 2 balls, np balls. Okay? If, for example, n is 1000 and p is, for example, 4 over 10, then we expect that in 1,000 balls, you have only 400 red balls, not, for example, 2 balls or 5 balls on the average. Then it means that the number of typical sequences is the number of ways that you can arrange these np balls in these n places. So the number of typical sequences is the combination of np from n. Right? This is the number of typical sequences that you have. So that source, in general, if you think of these balls as the letters of alphabet, which are coming out of a loudspeaker, for example, the average number of possible sequences that come from this loudspeaker is not the power n. It's the choice of np from n locations. And this number is this one. N factorial over np factorial over n minus np factorial, right? This is the probability of n ball, of red balls, and this is the probability of the number of blue balls. And if you now play with this Stirling formula, which is valid for large number of balls, then you will find that if this is the Stirling formula, n of n factorial is always equal to n and n of n minus n. This is the Stirling formula. You agree? It's usually written in this way, in text. N factorial, it's usually written in this way, e to the power n over n, something like that. Right? If I'm correct, it's something like that. And then if you take the logarithm, it will be appearing this way. N to the power n, no, it's not true. N factorial is equal to n to the power n, e to the power minus n. This is the Stirling formula. Right? And if you take the logarithm, you will find this. So if you use Stirling formula for these factorials, then you will find that this log of np choices from n is nothing but n times the Shannon h of p. It means that, where h of p is this one. It means that the number of typical sequences is not to the power n, it's 2 to the power n times h of p. And h of p is always less than 1. So, this is the full number of sequences, and the number of sequences, typical sequences that we deal with, is lower than that. It's 2 to the power n times h of x. And h of x is the Shannon entropy. That's why the loudspeaker on the source or everything that is broadcasting information for us, the number of all typical sequences that it produces is not something that we should deal with. We should deal with only the typical sequences, and the typical sequences are lower than the full number of sequences. It's lowered by this factor. 2 to the power of n times h of x is the number of all typical sequences. We have to store this one. So, again, the second thing. Okay. You have time for questions. Questions? Comments?
I have a question.
Yes.
What's the importance of having the typical sequences, the number of typical sequences? Why do we try to find that?
If I understand you correctly, maybe microphone can
my question is that why do you find why do you want to find the number of typical sequences?
Ah, yes, I see. I hope you can see this. Okay? Suppose that A, the probability of A, letter A, is 1/2. Or, for example, 1/3. The probability of the letter B is 2/3. Okay? And the source is broadcasting these sequences of letters of A and B, okay? Text, for example. Do you expect to see something like this? I say no. Right? It's very improbable that a sequence like this be produced by this source. It's very probable, it's less probable that the sequence of letters be something like this. Right? So most of the sequences, almost all the sequences that the source produces is those in which 2/3 of the letters, 1/3 of the letters are A in various places, and 2/3 of the letters are B. These are the typical sequences. So I claim that the sequence of letters that the source produces is not 2 to the power n. It's 2 to the power n times h of x. I should store this amount of information. I hope it will be clear, but we can discuss it. Any more questions, comment, or objection, or protest? Shall we go on? So the second Shannon theorem. So the first Shannon theorem states how much you can compress information, right? How much you can compress the Mona Lisa picture without losing the content. But the second important problem is that you want to communicate this information from one place to another place. You switch on your TV and you see the information of a football match in Spain. So information is transferred to you from one place to the other place. Information there has been compressed as much as possible. Then this information is transferred to you over long distances, via air, via cable, and so on. So the next important thing is that we want to transfer information from one place to another place, a communication channel. Here the Mona Lisa picture. Here is our communication channel. It can be air, free air, can be cables or fiber optics or anything like that. And in any information channel, in any channel, classical channel, there is a probability of error. You encode information 0, 0 goes inside the channel, and it flips by some probability, by some error in the air, to 1. Right? There's always error probability via the channel. The longer the distance, the higher the probability. Right? And then, if you do nothing, you will receive this picture. because there are always errors. So what you should do to retrieve the Mona Lisa picture in a safe way, you have to combat the errors in the communication channel. How do you do that? Right? This is the second problem, the most important problem. The best thing is to use some sort of encoding again. So instead of 0, 1, 0, now we are done with source encoding. We are done with compression. That problem was solved. Now we are dealing with transferring information. We want to transfer one of the zeros. The best thing is that you repeat. Instead of 1, 0, you send 3 zeros. Right? And then at the end, if you receive 0, 1, 0, you will say that this one is suspicious. It has been a 0, and it has been flipped. Right? You use the majority rule, and then you flip the 1, 0, and then you retrieve the 0 again. Right? If you want 2 1s, then you flip it to 1. And then you can now calculate the error probability. The error probability before was P. Now the error probability has become lower, because the error probability is that 2 bits flip or 3 bits flip. 1 flip you can deal with, you can correct. But with 2 flips and 3 flips, you make errors. And the probability of these errors is this one, 3p squared. And it's lower than p, because p is a small number. P is 1 over 10, for example, 1 over 100. And when you square it, it becomes lower and lower. So the probability of error becomes lower. But the problem is that we have paid a price. For lowering the error, we have paid a price. What is the price? I can block you to see this. What is the price? You have lowered the rate of information transfer because you send 3 bits, right? But actually you are sending 1 bit of information. The 2 bits, the 2 extra bits are correcting the errors, right? But note that you have not achieved 0 information communication, 0 error communication. There is still some probability of error. It's 3p squared, right? You do not want to see a music in a distorted way with a low error. You do not want to see a football match with some error. You do want a football match with 0. You do want to hear music with 0, to see a movie with 0. You do not tolerate even a small error. So how do you go to lower this rate of error? How do you do that? Any suggestion? With encoding of 1 bit to 3 bits, we lower the error rate. Any suggestion for reducing the error?
You should put minimum bits, not 3.
Not 3, but 5, for example. 5 is okay.
Yeah.
Instead of 3, we encode to 5. Right? It's a good strategy. And again, we use the majority rule. Now, what is the probability that Steve may make an error? Now, instead of 2 bits, if 1 bit flips, we can deal with that. We can correct it, because we use majority rule. If 2 bits flip, again, we can correct it. We make an error if 3 bits flip, or 4 bits, or 5 bits. Right? And the error probability is low. Because to flip 3 errors, the error probability instead of p squared is p to the power q. And it's lower. If p is equal to 1 over 10, p to the power 3, which is the probability of flipping 3 bits, is 1 over 10 to the power 3, which is 1,000. 1 over 1,000, which is low. So in this way, you can lower the probability, right? Are you satisfied with this? Do you like to see a football match with a probability of 1 over 1,000? To hear music with probability 1,000? No. Nobody. Nobody likes it. We want zero probability of error. But if you follow this argument, it means that you are paying a high price. To lower the probability that encoding 1 to 5, you are reducing the rate from 1 to 1 over 5. Right? So you are reducing the rate more and more. It means that if you draw a plot in which this axis is rate and this axis is error probability, you decrease the error probability. At the same time, you decrease the rate of information transfer. Right? And if you want zero probability of error, the rate of information transfer is also zero. So you have to wait for 1 year to see a football goal, for example. Because the error probability is zero, but the rate is also. Okay? So you see the problem, the main problem. And you can appreciate why the work of Shannon is so important. He proved that this is not necessarily the case. He proved that you can have an encoding of information so that this curve is not like this. This curve is like this one. Like this one. You can have zero probability of error, but with a rate which is not zero necessarily. There's a green area here. You can transfer information with zero probability error if your rate of transfer is below C. C is called the capacity of the channel. Right? Below the capacity, which is, there is a certain mathematical formula. Yeah? You can transfer information with zero error. Above that, you will never be able to communicate information in safe form. So every channel has a capacity, you have to calculate. This means that if you information transfer is below C, below the capacity, you can convert this Mona Lisa picture to a sequence of zeros and ones. You encode in a specific way, and you retrieve the Mona Lisa picture in safe form. But if you use a higher rate of information transfer, higher than C, then you will lose the picture. You will update this one. There's no way to communicate information in safe form higher than the capacity of the channel. And there's a formula for the capacity of any channel. It's not easy to calculate these capacities, but there is a certain formula. How much time I have? I think that I'm finished.
10 minutes.
10 minutes.
10 minutes from now?
Yeah.
Are you sure?
Are you sure? Yes.
No, it's your time's over, but time's over.
Time is over, but just feel free to.
Yes, it's a good idea, but as a speaker, you should also think about the faces of the audience. Sometimes they look at their watch. You have heard that for a speaker, time goes very fast. For the audience, time goes very slow. Right? So we make a compromise. And I will show you a few more slides and then stop. There's a famous saying by Eddington, Arthur Eddington, you know, the famous astrophysicist. He has said that I'm not angry about those people who look at their watches, but I'm angry about those students or audience who shake their watch to see if it's slipped or not. So I hope that this is not the case with you. Okay, this is the whole communication channel. Here you have the source. This is the combination of the two theorems of Shannon. Here you have the source, A, B, C, D, etc. In this block, which is called source encoded, you convert them to a sequence of zeros and ones in the most economic fashion. You compress them. Again, here, the Shannon entropy. In this part, you encode these, which is called channel encoding, to combat the errors. Right? So this is for the compression, this is for the come back over the error. Then the sequence of errors come to the classical channel, and we decode it here to the sequence of zeros and ones, and to correct those zeros which have been flipped or ones which have been flipped, and then we decode again to A, B, C, D, or whatever it is. Music, sound, or anything. This is the whole. Again, the formula that Shannon has for the capacity of the channel relies on the concept of typical sequences. Again, typical sequences always play a very important role. And what is the basic idea? The basic idea is that suppose that the probability of error in each bit is P, right? The probability of each error. Do you expect that all the bits flip? All the bits. Do you expect? No. Do you expect that only one bit flips? No. You expect that the average number of bit flips is n times p. Not every bit flips. Because if the probability of a bit flip is p, on the average you will see np bits which have been flipped. So the number of typical errors is not 2 to the power n. It's 2 to the power of n times h of p. With the same argument. This is the number of typical errors. Right? And this means that if from the whole code space you choose these ones, right? And then you choose these red ones, these green ones as your code words, right? And draw a sphere around that. This sphere contains all the typical errors, right? There's a volume in each sphere. Each code word typically goes to here, or here. It doesn't jump from here to here, because it's not a typical error. The typical errors are inside each sphere. So the best thing to do is that this is the number of code words that you are using. I have chosen 2 to the power of k code words. The number of code words, the number of errors in each sphere is 2 to the power of n h of p. And in order to combat the errors, these spheres should not overlap. So this number should be less than this. It means that this inequality should be satisfied, and it means that the number k, which is the number of bits that I'm using to encode for this transfer, suppose that I'm using such encoding, previously I encoded 1 bit into 3 bits, right? And then 1 bit to 5 bits. But we saw that this is a failure. Now I encode k bits to n bits, right? And then this inequality should be satisfied. The number of all possible code words that I have here in this column is 2 to the power k. The total number of possible code words is 2 to the power n. Each code word can be moved inside the sphere. The volume of each sphere is 2 to the power n hp. It means that this inequality should be satisfied. And this means that the rate of information transfer should be less than 1 minus hp. This is the capacity, because we told you that the rate of information capacity with zero error means that these spheres do not overlap, should be less than R, or less than C. So this is C. This is the capacity of the channel. Yes, please.
To decide the code words number, I think when we calculated this one, it is dependent with the data size.
Say it again, please.
When we find the code size key number,
Mm-hmm.
we used to the entropy in the data,
Mm-hmm.
but we don't know which data will come. It's
exactly, that's a good question. Suppose that you receive this one, this red one, okay, right? Then you correct it to the center of this sphere. If you receive this one, again you correct it to the center of this sphere, because you guess that it has been most probably this central code number, code word, which has been converted to this one. No code word jumps from here to here. That's the way that you correct, right? And the argument goes. And now with this calculation, which is still oversimplified, we come to the completion of the two theorems of Chang and the two pillars of information theory, classical information. I stress again that all these arguments were intuitive. If you are interested in this topic, you should consult a specialized book on information theory. There are lots of books, and I hope that I have conveyed to you the basic ideas. And then in the afternoon, we repeat these things for quantum communication with quantum information. It will be slightly more complicated than this, but I hope that you will not be bored. This is the end of part one. Again, we're covered. Thank you very much.